Chapter 2 Internal Structure of Earth and Plate Tectonics 2.1 Internal Structure of Earth. Welcome back to Chapter 2 Internal Structure of Earth and Plate Tectonics. The Earth is not a homogeneous ball of rock. The Earth has structure with several distinct layers that move and cause our Earth to be the way it is. These layers stretch from the very core of our Earth out to the crust, with which we are so familiar with. The layers are differentiated in a couple different ways. One way is by composition, or in other words, density. Another way is by physical properties such as liquid, solid, and mostly solid, partly liquid. Because the layers are differentiated by both composition and physical properties, things get a little confusing towards the outside of the Earth, but I think you can handle it. This is a simplified diagram of most of the layers we are going to discuss in this chapter. You can see how the layers get a little confusing at the top, so we will start at the core. The inner core is solid, about the size of the moon and the temperature of the sun. It is composed mostly by iron, about 90%, but also contains other elements such as sulfur, oxygen, and nickel. The density varies from about 13 grams per cubic centimeter at the core, but with an average of about 10.7 grams per cubic centimeter. The outer core is liquid and thicker than the inner core, but the composition and density are very similar. The mantle is mostly solid, which means slightly liquid. It is about 3,000 kilometers thick and composed primarily of iron and magnesium-rich silicate rocks. An iron-magnesium-rich mineral is olivine, which has a nice green color. The average density of the mantle is 4.5 grams per cubic centimeter, which is about half the average density of the inner and outer core. On top of the mantle is the crust. This is the outer rock layer of the Earth that we are familiar with. Its average density is about 2.8 grams per cubic centimeter, again about half of the layer below it. The crust has oceanic crust and continental crust, which are quite different. The oceanic crust is primarily below the oceans. Hopefully that makes sense. The ocean crust is thinner and slightly more dense than continental crust. The continental crust is thicker and slightly less dense. When these two types of crust meet at a convergent plate boundary and one plate subducts beneath the other plate, which plate do you think will subduct? The thicker, less dense continental crust, or the thinner, more dense oceanic crust? If you thought the oceanic crust will subduct beneath the continental crust, you are right. Way to think. If you thought it the other way around, you still get brownie points. But can you see that the thinner and heavier crust would prefer to sink under the thick, lighter crust? Think of hot cocoa made with milk and marshmallows. Think of the thin milk skim on top versus the thick, fluffy marshmallow. Unless you push the marshmallow down, would the marshmallow ever go beneath the milk skim? Back to the Earth's crust. Which type of crust do you think is on average older? The crust that always subducts, or the crust that always stays on top? If you thought that the crust that stays on top should be on average older, you are right. The continental crust is older because it does not easily get subducted and destroyed, i.e., melted. So on average, the oceanic crust is 6 to 7 kilometers thick and less than 200 million years old, as compared to the continental crust, which is on average 35 kilometers thick, but up to 70 kilometers thick, and can be several billion years old. Between the crust and the mantle is the Mohorovic discontinuity, or the MOHO for short. The MOHO separates the lighter crustal rocks from the more dense mantle. It is 5 to 10 kilometers below the ocean floor and much deeper beneath the continents, 20 to 90 kilometers. At this density change, seismic wave velocity changes as depicted in this picture. In the crust, the primary P wave travels about 7 kilometers per second. In the mantle, seismic waves can travel faster, and the P wave speeds up to about 8 kilometers per second. So that is how the Earth is layered, based on composition, i.e. density. There are a couple more layers, important layers, that we need to identify based on physical properties. The lithosphere and the asthenosphere. Lithos is Greek for stone. The lithosphere is the cool, strong, outermost layer of the Earth. Just like the crust, it is rigid, it is solid. It is thinner under the oceans, about 3 to 120 kilometers thick, and thicker in the continents, 20 to 400 kilometers thick, just like the crust. But if you've been comparing thickness, you can see that it is thicker than the crust. You're right. The lithosphere is thicker than just the crust. The lithosphere is not only comprised of the strong, rigid, cool crust, but also the tippy-top, rigid part of the mantle. The asthenosphere is also in the top portion of the mantle, directly below the lithosphere. Asthenos is Greek for weak or without strength. It is not rigid. It slowly flows like a putty under pressure. It is generally between 100 and 200 kilometers below the surface of the Earth, but can be up to 700 kilometers deep. That's deep, but the mantle extends much deeper, about 3,000 kilometers below the surface of the Earth. So in summary, the lithosphere is strong, rigid stuff. It includes all the crust and the tippy-top part of the mantle that is also rigid. It includes none of the atmosphere. The asthenosphere is weak and flowy. It is directly below the lithosphere, but still in the top portion of the mantle. Let's draw the internal structure of the Earth. Get out your pen and paper and draw too. First, pause the discussion and see if you can correctly draw the inner core, outer core, mantle, crust, lithosphere, and asthenosphere. Now it's my turn. Inner core, outer core, mantle, crust. Lithosphere, asthenosphere. Mistakes most often include incorrectly drawing the lithosphere and the asthenosphere. Remember, the lithosphere includes the crust and the tippy top part of the mantle, and no atmosphere. Remember, the asthenosphere is directly below the lithosphere, but still in the top portion of the mantle. The asthenosphere does not extend very deep into the mantle. Now, these layers don't just sit there. The Earth is dynamic and always changing and moving. Movement in the mantle and asthenosphere causes the lithospheric plates to move. The movement is powered by convection and is illustrated in this picture. Earth's internal heat causes magma to heat up and become less dense. The less dense magma rises towards the surface, cools, and then falls back down to the outer core to be heated up again, becoming less dense and rise, etc. Where the hot magma rises, there is a ridge. A classic example is the Mid-Atlantic Ridge, and some of the magma gets to the surface and becomes lava. The lithospheric plates are divided here and diverge away from each other. Where the cooler magma sinks, the lithospheric plate sinks down, subducting, causing a trench. A classic example is the Marianas Trench. The lithosphere is dragged about on the moving asthenosphere, which flows on the order of centimeters per year. The heat source for all this convection is the mantle. The heat source from all this convection of the mantle is from formation of the planet, core crystallization, and radioactive decay of unstable isotopes. The same type of convection occurs in your pasta pot as seen in this picture, though the heat source is more mundane. Water is heated at the bottom of the pot where it is close to the stove element. The hot water rises, then cools, and then sinks to be warmed up again. This forms a convection cell. So how do we know about the internal structure of the Earth anyway? I'll tell you in a bit.